previously we saw that we could find the area of a polar region like the one I'm displaying in the upper left corner by dividing that region into small, approximately rectangular regions. Those regions having an area delta A sub ij. And although they're not exactly rectangular, if we use small enough regions, then they will be approximately rectangular and give us a good approximation of the area of this polar region. Now, if you look to the right, one of those areas, delta A sub ij, we can think of as being just a length times a width. The length is going to be this distance, r times the angle delta theta. We got that by our geometric formulas for arc length of a sector of a circle. And then the width was delta r. So the area of our region was r delta theta times delta r. That was just for one of those approximate rectangles. We could sum up over many of them to get the area of the entire region. And so we'd be summing up over r sub ij delta r delta theta. But if we let delta r and delta theta go to 0, so that we're using more of these approximate rectangles, but because they're smaller, our approximations are going to get better, then we could look at this as being a double integral over r dr d theta. And that led us to the conclusion that when looking at dA for our double integrals, in rectangular coordinates, it's dx dy, but in polar coordinates, it's r dr d theta. Now I'd like to do something very similar, but with spherical coordinates. So what we're going to do is break up a spherical region into chunks that are approximately rectangular prisms. And we're going to sum up over all of those approximate rectangular prisms and maybe calculate the volume of, say, an entire sphere. So these approximate rectangular prisms I'm going to trace out like this. So we have here some sort of height, and then I'm going to call that the width, and then I'll call that the length. And so we want to find the area of this piece, which is easy to describe in spherical coordinates. Sorry, the volume of that piece, which is easy to describe in spherical coordinates, so that we can then sum up over those little pieces of volume. So a little chunk of volume, which I'm going to call delta V, so that's going to be this chunk of volume, okay, can be described as being a length times a width, and then times a height. Now the easiest piece to describe is going to be the height. The height is going to be delta rho. The width, which is this small piece right here, that is the same width as its projection in the xy plane, and that is the arc of part of a circle. And so we need to know the distance here, and then if we multiply that distance by delta theta, that should give us this little bit of arc length. That distance we know from our discussion of spherical coordinates. When we project rho into the xy plane, we just get rho sine phi. And so this distance right there is going to be rho sine phi delta theta. And so that's going to give us the same thing up there. So we're going to have rho sine phi delta theta for the width. And then finally, for the length, again, we're looking at an arc length, so we just need to know this distance. But this distance is going to be rho. And then the angle here is going to be delta phi. So we get rho delta phi. So if I kind of rearrange this, this ends up being rho squared sine phi delta rho delta phi delta theta. And so that is the approximate area of that rectangular prism. I'm going to want to then sum over all of those approximate rectangular prisms to give me the volume of the sphere. So the volume of the sphere, we're going to describe as a triple sum. So we can sum over different rhos, phis, and thetas. And we're going to sum up a delta v sub I, j, k. So I'm going to write this out. This is going to be a triple sum. And then we want to sum over rho sub I, j, k squared sine of phi sub I, j, k. And then we've got delta rho delta phi delta theta. So we're going to sum that to get an approximate volume of the sphere. If we want to get the exact volume of the sphere, well then we're going to want to take a limit. So we're going to want a limit here. In that limit, we're going to want to take delta rho, delta phi, and delta theta all going to 0. And so what that will leave us with is a triple integral of rho squared sine phi, and then delta rho delta, that's going to be d rho d phi d theta. And then it's just left to finding the limits of integration. If we're going to calculate the volume of the sphere, maybe we'll let that sphere have a radius r so that rho goes from 0 to r. And then we know from spherical coordinates that phi can go from 0 to pi, and then theta can go from 0 to 2 pi. And so the exact volume of the sphere, because before we had an approximation, the exact volume of the sphere is given by that limit, which of course is an integral. Okay, so let's actually do this calculation for the volume of a sphere. So the volume of a sphere, okay, is going to be that triple integral. And I'll notice that I have a function of rho times a function of phi, and then also times a function of theta, but that function is 1. So I can actually split up this integral like we've done before. So this is the integral from 0 to 2 pi d theta, the integral from 0 to pi of sine of phi d phi, and then the integral from 0 to r of rho squared d rho. So the integral from 0 to 2 pi of d theta is just 2 pi. And then we're going to get a minus cosine of phi evaluated between 0 and pi for the antiderivative of sine of phi. And then we're going to get a 1/3 rho cubed from 0 to r for the antiderivative there of rho squared. Okay, so this becomes 2 pi times minus cosine pi, so that's 1. And then that's minus cosine of 0. So minus, sorry, a negative cosine of 0, which is minus a negative 1. And then here I'm going to get 1/3 times r cubed. So I'm going to get 2 pi times 2. So that's going to be 4 pi over 3 r cubed. And that is what we expect for the volume of a sphere, 4/3 pi r cubed. Okay, so what did we learn from this? Just a little summary here. When changing to spherical coordinates, then dx, dy, dz we can write as rho squared sine phi d rho d phi d theta. And that will give us our spherical coordinates change when we're doing triple integrals. Now, something that's useful is the integral from 0 to 2 pi, the integral from 0 to pi, sine phi d theta. That comes up a lot. Sometimes we have these radially symmetric functions. You'll see that that integral came up, in fact, right here. That was this double integral. Okay, and if you follow that through, you'll see that that double integral was, in fact, 4 pi. So it's sometimes nice to remember that this particular integral, when it comes up, is equal to 4 pi.